Okay, so we are in Statistical Rethinking, second edition. We are in Chapter 8, Question 8M4. So before you get into any of this, make sure you've installed and loaded the Rethinking package. And let's begin. Okay, where are we at here? Okay. So we're going to repeat an analysis that was done in this chapter on the tulips. So in that analysis, we were looking at bloom size as a function of water and shade. And there was also an interaction term in there between water and shade. Okay. And so we're going to repeat that. And this time we are going to constrain the model so that the effect of water is to always produce bigger blooms, and the effect of shade is always to produce smaller blooms. Okay, well, let's do that, and then we're going to plot these the implications of our prior. Okay, so the first thing to address is, why would we want to constrain the priors in this way, right? Well, presumably it's because we know something, or at least we are assuming something that that makes these priors make sense. Okay, but I can imagine scenarios where more water does not always lead to bigger blooms, or that more sunshine leads to bigger blooms, right? I can imagine where you have excessive water or sunlight that maybe harms or kills a plant. I'm not a plant person, but I can imagine that could be the case. Okay. And so this is one of the strengths of well, maybe not Bayesian analysis, although it makes it very explicit, but of stating up front the assumptions that you're using in your models. And Bayesian analysis always makes this very explicit as long as you're sharing your model, because the assumptions are just played out right there in the priors and in the construction of the model, etc. Okay. So to get these models going, we need to go back and I'm just copying and pasting what was presented in the book, but we're using a standardized blooms and then centered water and shade here. Okay. So here is model M85 in the book. Okay, and so we don't need to run this, but this is the thing that we need to modify. Okay, remember, again, we are trying to constrain BW, the effect of water, to only be positive, and the effect of shade to only be negative. Okay, and then we'll talk a little bit about what that means for the interaction. Okay, so there's a few ways that we can add these constraints, and one is to simply add the constraints argument to your model right here. Okay, unfortunately with QAP, that little function does not work. That argument does not work. And so we have to wait until, I think, maybe starting next chapter, when we get into Markov chain Monte Carlo, where we will instead use a command called ulam. But it's just good to know that that this is an option when we get into using ulam or Markov chains Monte Carlos. Okay. So instead of just adding this, we're going to have to fiddle with the model here. Okay, so there's a few ways that we can do this, and so we'll just explore one. So remember, we want BW to be positive, and one way we can do that is to just use a non-negative distribution, a distribution that cannot entertain negative values. Okay, and probably the one that we're all familiar with is a log normal distribution, or most likely to be familiar with, which is just a normal distribution. The log of a normal distribution. Okay, so the command for that is dlnorm. Okay, now for the effect of shade, remember, we want this to always be negative. Well, one thing that we could do is again use a non-negative distribution, the dlnorm, but then in the linear model, to ensure with a negative here, when we're defining our linear model, to ensure that BS is negative, by instead of adding it, we are subtracting it. Okay. And now we need to think a little bit about the interaction term. How do these two constraints on the effect of water and the effect of shade, how do those conspire in the interaction. And so how should we constrain the interaction? Okay, well, one way that we can think about the interaction is that the effect of shade decreases the effect of water. Okay, so we need to constrain BWS, the interaction, also to be negative, so we can use the same two tricks that we used for BS. Okay, so now when we put all of that together, here is what our model looks like, right? So we have DL norms for our coefficients, except for the intercept, okay, which we're leaving alone. And then we are subtracting, in other words, forcing to be negative BS and BWS. Okay. Now, I don't know what these values should be at this point. We could get some good guesses because you could actually figure out what the mean of the log normal distribution is, and how it's, you could figure out some of the properties of it if you just go to Wikipedia, for instance. In fact, let's do that. Give me a second here. Here, I'll pause this as I go there. Okay, so I come here to the Wikipedia page for the log normal distribution, or whatever resource is good, and we see that we can calculate the mean, and the mean is not quite mu, right? It's mu plus some contribution of the standard deviation. But anyway, we could use these and do some arithmetic to try to figure out what would work. Okay, but rather than do that, we're just going to kind of trial and error it instead. Okay. So let's just try this. Let's just run this model without having modified the values in these parentheses and see what happens. Okay, so I've ran the model, and now if I want to get at the priors, I'm going to call this object priors, and I'll use extract prior, and then the model that I'm referring to. Okay, this is part of the Rethinking package, and then we'll see what that looks like. So when I run this, so this gives me a bunch of, well, it gives me a list. And then I have 1,000 values for the parameter values of BW and 1,000 for the parameter values of BS, and so on and so forth, right? So these are, again, just the contributions to our linear model, as well as, our standard deviation. Okay. So now what we need to do is we need to plot the implications of these priors. Okay, so we need to find a way of looking at the relationship between blooms and shade and blooms and water. And then whenever we're looking at one of those relationships, say bloom and shade, we need to hold the other constant, right? So the effect of shade on blooms holding water constant, and the effect of water on blooms holding shade constant. Okay, and so the book, in fact, with this example in the book, in section 8.33, uses what do they call it? The triptych plot idea. Okay, and so I'm just copying that code. That's all that this is right here. But I'm just copying that code. But there's an important modification that you have to make, which is you have to add this line right here. Okay, so in this for loop here, we're normally looking at, or it's using the link function, and the link function normally just looks at the posterior of your model. But I need to tell it, no, look at this object called priors. Don't look at the actual posterior. Okay. So anyway, we're going to run this, and let me open this up in a different window here. Okay. So we have three different plots. Okay, shade equals -1, shade equals 0, shade equals 1. Okay, and we notice that our priors are not doing a great job here, especially here. Not great here, but we're missing wide swaths of the data with our priors. Okay, so now we don't need our priors. In fact, we don't really want our priors to completely overlay the data. It should not be perfect fits. But our prior has to at least entertain values that our data actually lives in, okay? And so this is not doing a great job here, all right? So we need to modify this. How are we going to modify this? The first thing that I notice, especially right here in shade equals -1, is that the slope for BW is entirely too sharp. And so the slope needs to come down. We need to favor prior values with a lower slope, smaller slope, okay? And so that's what I'm going to do. I also notice how radical the shift is in these slopes as I move from left to right. And so probably the effect of shade is also too much, okay? And so, so what I'm going to do is so instead of having 0 here for these DL norm priors on our coefficients, I'm going to make it smaller, so I'm going to have -1, okay? And so I'm going to just run the same code. I'm going to extract and then plot everything all in just one code block here. Okay. Let's open this up in a new window. Okay. So this is doing better. Okay, but we're still so notice first of all that the slopes are more moderated. You can see it here and here in shade equals 1 and shade equals 0, but we're still missing quite a bit of data. So I'm just going to continue on that trend again, and I'm going to make it a little bit smaller. Okay, so now I have even smaller slopes, or favoring even smaller slopes. Okay, so I'm going to run this. Okay, and now our priors are probably doing a decent job. Okay, we might still be missing some here, and so we could continue playing with this if we wanted to, but that's, let's just stop it there. And so the important thing about our priors here, again, is not that it's fitting the data, but that it is allowing for values in our posterior where the data live. Okay, so so just for kicks, let's actually look at the posteriors of these 3 models, right? That have the 3 different sets of priors. Okay, and just look at how the posteriors are being affected by the priors here. All right, so so now I'm extracting samples, which extracts from the posterior of the 3 models. Okay, and then I'm going to plot it in a big 3x3 plot here. Okay. Okay, so let's open this up in a bigger window. Okay, so here's our first set of priors, our second, and our third. Okay, and certainly you can see that as we are moving down, we are, well, at the very least you can tell that our priors are having an effect on the fit of the model. Okay, or on on the posterior of the model. So anyway, I guess that's where we will call it here, and yeah, I'll see you next time.